Hello and welcome back to another video on 8086 microprocessors. Today we are going to be discussing different kinds of memory architectures that are possible. First, let's look at the kinds of memory devices that are available out there. The two big kinds, there is a read-write kind of memory devices and there is the read-only kind of memory devices. Read-write popularly is called RAM, and there are two kinds of RAM. There is a static RAM and there is a dynamic RAM. These are volatile read-write memory chips. What does it mean to be volatile? Volatile means the memory content is maintained as long as there is power to these chips. So if all of us know that if you remove power from a RAM device, a random access memory device, the RAM loses all content. That's why it's called volatile. Read-write memory also has a non-volatile kind, and there are many kinds of this. There is E2PROM, there is EEPROM, there is flash memory, so on and so forth. These kinds of devices can record data, can re-record data over and over again and will not lose the information even if you remove power. That's why they are called non-volatile. On the read-only category, you have only the non-volatile kind. So there is no volatile read-only devices. And in the non-volatile kind, it's called ROM, read-only memory. Quite simple. There is something called a PROM, programmable read-only memory, and these are devices that you can program using electrical programmers, and you can program them once. When would you use volatile? When would you use non-volatile? Volatile memory is typically used for storing temporary data, for storing intermediate values, whereas non-volatile memory is used for storing programs, it's used for storing constants belonging to a program, so on and so forth. So typically ROM and EEPROM, E2PROM hold the program in a CPU system. Let's understand how to use memory within the 8086. Now remember, the 8086 is capable of addressing 1 megabyte of memory, starting at address location 00000 hex all the way up to 0FFFF hex. This is 1 megabyte. In this 1 megabyte memory map, the bottom region of memory starting at 0 must have physical memory. The reason is the interrupt vector table resides at this location. Similarly, the top of the memory location starting downwards from FFFF hex must have physical memory. The reason, because at the time of reset, the processor automatically jumps to FFFF0 hex and starts executing from that location onwards. Obviously, if there is no memory at the top of memory bank, the processor has nothing to execute and nothing happens within the system. Other than these two constraints, you as a designer can choose to locate memory within the 1 megabyte of space anywhere. It could be ROM, EEPROM, RAM, it doesn't matter as long as it is within this 1 megabyte space. Let's look at the hardware organization of memory within the 8086. The 8086, remember, has a 16-bit data line, D0 to D7, D8 to D15. You as a designer have to design the memory location such that you have an even memory bank and an odd memory bank. The even memory bank resides on the data bus D0 to D7. The odd memory bank resides on data bus D8 to D15. Both the memory banks have common address lines, right? There's just A1 to A19, they have got the common address lines. Both memory banks therefore rest on one address line. How does the processor address the even versus the odd memory bank? It uses A0 to address even memory bank, and it uses another signal called BHE bar, byte high enable bar. So the processor will automatically pull byte high enable bar low when it wants to access the odd memory bank. So using A0 BHE bar, you address either the even memory bank or the odd memory bank. Using address lines A1 to A19, you address a specific location within those memory banks. And if it's even, you get data on D0 to D7. If it is odd, you get data on D8 to D15. Now let's look at a few common memory architectures. The first one is called absolute memory decoding architecture. And the diagram explains this architecture to you. What happens here is the set of address lines A1 onwards up to A13, A12 depending on the size of the memory is used to decode individual memory locations within the bank. The set of address lines A14 onwards is used to then generate a chip select. So depending on what you have chosen as the location of these memory banks, you have to appropriately program these address lines. In addition, M/IO bar, read bar, byte high enable bar and A0 are used to access memory as a read or a write and the odd or even memory banks. This is called absolute memory decoding architecture. The next one is called linear memory decoding architecture. In this diagram, you will see what this is. This is used for very simple memory architectures. It cannot be used for more complex systems. In this case, the line A19 is used to generate the chip select for the device. Of course, you still got M/IO bar, you got read bar, write bar, and you got byte high enable bar and A0 to access the odd and even memory locations, and whether it is a read or a write operation, and the fact that it is a memory or an IO operation. The third kind of memory architecture is called the block memory decoding architecture. As the name suggests, in this architecture, you access blocks of memory. Why would you do this? So suppose you have E squared PROM in your architecture, in your design. You got ROM in your design. You got RAM in your design. You can access each of these kinds of memories as blocks of memories. And the way it works is you use a decoder, and the decoder will help you select one block of memory or another. And that's the way it works. So in this example, the chip select enable is either for EPROM or for the RAM, based on whether you're talking about Y7 or Y0 from the decoder. All the other parameters are the same. You still have A0, you have byte high enable, you have the memory/IO bar, you have read bar and write bar. So the rest of the design of this memory architecture is the same. Advantage is you can access block by block of memory within the system. Useful for very complex architectures. I hope this gave you a flavor for various kinds of memory architectures. It gave you a flavor for how the 8086 accesses memory, the fact that there is an even and an odd block, etc. I would urge you to read up much more about these kinds of memory architectures. This is not the complete superset. There are other kinds of memory architectures, extremely complex architectures for more complex systems. I would also urge you to understand how the 8086 actually does generate these bus signals. We talked about bus signal diagrams. You should understand how it happens for these kinds of memory devices. In our next video, we're going to be talking about how to interface IO devices to a 8086. Till then, happy memorizing. Thank you very much.